VLSI Data Conversion Circuits, Lecture 2. So yesterday we saw that this whole process of data conversion involves a combination of anti-alias filtering, and then you have sampling, which quantizes time, and then you have amplitude quantization. So the combination of sampling plus quantization is called analog to digital conversion. And this typically happens on the input side of a system, where you need to take signals coming from sensors and interface them to a digital state machine. That could be a DSP, a microprocessor, whatever. On the output side, we have what is called digital to analog conversion. We were discussing this at the fag end of the last class. So where the idea is that you have a sequence of numbers represented in digital form, and you need to put out an analog waveform which corresponds to this discrete time sequence. Okay. So for example, if the discrete time sequence was like this, the x-axis is n. So when you have discrete time, the independent variable is just the sequence number n, and there are, the y is the amplitude. Okay. The amplitude is basically no units. Okay. Now you want to convert this into an analog waveform. When you have an analog waveform, the independent variable must be time, and the dependent variable on the y-axis, the units can be either voltage, current, charge, whatever, any physical quantity that you may want to represent. So one example of an analog waveform which kind of mimics the information content in the discrete time signal is shown below. And as I said, this is only one possibility. Several other possibilities exist. We will come to them when in a little later. But this is the basic idea. So in other words, while you understand that this is discrete time and this is discrete time and this is continuous time, you see that this waveform here has some semblance to the set of discrete numbers. A gadget which accomplishes this objective is called a D2A converter, and as it turns out, these amplitude levels are actually quantized simply because they all depend on the register lengths inside a DSP. Okay. So this is the digital to analog converter, often referred to as a DAC. This is the, you understand? The next thing is that since we are interested in sampling a signal before we quantize, it's fair enough that we wish to find out what the spectral properties of the signal when it's sampled are, when compared to the signal that we are sampling. Spectra of sampled signals. So the continuous time signal is denoted as x of t, and it has a Fourier transform x of j omega. Alright. When you are dealing with continuous time and discrete time signals, the continuous frequency variable is denoted by capital omega, and the discrete time frequency variable is denoted by small omega. Okay. And this is standard practice in all signal processing textbooks, and we will continue to use the same convention. And x of j omega is basically, the usual Fourier transform formula. e to the minus j omega t dt blah blah blah. So this is the Fourier transform of x of t. And since it's always nice to look at a picture, the spectrum could look like this, for example. I'm just plotting the magnitude. All right. Now, if I sample this x of t, I will get a sequence of numbers, and that sequence will be x of kt, where k is an integer. Correct? T is the sampling period, and 1 over t is the sampling rate. This x of kt, which is a sequence of samples, is obviously a discrete time signal. And the discrete time signal will have its Fourier transform. So x of kt transforms to x of e to the j omega. Okay. This is the discrete time Fourier transform of the sequence x of kt. All right. And a fair question to ask is, I know x of t and thereby x of j omega. I know the sampling rate. So what can I conclude about the spectrum of the sample signal when compared to given the spectrum of the continuous time signal and the sampling rate, what would be the spectrum of the sample signal? This is all mostly review material, because I'm sure you've all done this in earlier classes. So I'm going to zip through it. And the way this is done is to go back to basic signals and systems and consider the following. So you take the continuous time signal and multiply it by a Dirac delta train. All right. A Dirac delta train is basically a series of delta functions with its periodic in time with a period of t. All right. And xs of t, that's the multiplied waveform, which is the product of the continuous time signal and the Dirac delta train, is x of t sum over k t minus k. Right? Now, this, which therefore means that the spectrum of xs of t is given by, when you multiply two signals in the time domain, their frequency spectra are convolved. Okay, so 2 xs of j omega is nothing but 1 over 2 pi x of j omega convolved with the Fourier transform of the spectrum of the delta train. And please recall, the delta train transforms to 2 pi by t sigma delta of omega minus 2 pi by t. Sorry, 2 pi times kt, right. The 2 pi by t is coming because we are talking about radiant frequency. You know, the spectrum of xs of j omega is simply the convolution of x of j omega with 2 pi by t summation delta of omega minus 2 pi k by t. Does it make sense? Straightforward. Which means that xs of j omega is 1 over t. You convolve these two, it's simply x of omega minus 2 pi k by t. Does it make sense? No, it's just omega, right? Whether I can drop the j, isn't it? Okay. So, alright. Now, we know that x of e to the j omega, that's the discrete time Fourier transform of the sample sequence, is x of n, which is x of kt e to the minus j omega n times, j omega k So this is what we want to find. That's the discrete time Fourier transform of the sample sequence in terms of x of capital omega. That's what we are after. Okay. So if you compare these two expressions, so this is what we have learned so far. Xs of t is x of t delta of t minus kt, which is equivalent to saying it is nothing but x of kt delta of t minus kt. Correct? Therefore, it follows that xs of j omega is nothing but xs of t. That's the definition of the Fourier transform of xs of t. And that we found to be equal to this chap. Alright? And what is xs of t e to the minus j omega t? What is this? It's nothing but, if you take the Fourier transform of this on both sides, what would you get? Xs of j omega is nothing but sigma x of kt e to the minus j omega kt. Correct? I mean, this is nothing but a sum of many terms, and I'll take the Fourier transform term by term. Each term is x of kt delta of t minus kt. So, its Fourier transform must be x of kt multiplied by the Fourier transform of delta of t minus kt, which simply is e to the minus j capital omega times kt. Correct? So, these two expressions are equivalent. Okay. All that we have done is we have found the Fourier transform in two different ways. And what we are after is this chap here. This is what we want to find. So can you see a correspondence between the two? We want this, okay, we have found this, and this happens to be the same as this. Pardon? So, if I simply replaced, noticing the fact that if I look here and here, all that there is that if I found excess of j omega and replaced, so to find x of j omega, I say find excess of j omega, then I replace omega t by small omega. Is this clear? See, I see many blank faces, so let me go over this again. What am I trying to do? I'm trying to find the discrete time Fourier transform of a sequence obtained by sampling a continuous time signal. The continuous time signal has got a spectrum, some x of j omega. I realize that excess of j omega is this quantity, alright, and which also happens to be equal to this. And what I am interested in finding is x of kt e to the minus j omega k. So looking at these two expressions, one can conclude that if you want to find the discrete time Fourier transform of the sequence obtained by sampling a continuous time signal x of t, then I find the Fourier transform of the continuous time signal multiplied by a delta train, which happens to be this guy, and replace capital omega t in that expression by small omega. Does that make sense? So after all this math, let's figure out what it really means. In other words, x of e to the j omega is nothing but 1 over t summation x of omega by t. If capital omega times t has to be replaced by omega, it means that capital omega has to be replaced by small omega by t minus 2 pi k by t. And as you all know, this chap here is periodic with the period 2 pi. Once you sample a signal, it's a sequence of numbers. There is no notion of hertz or radians per second. Okay. So the discrete time frequency lies in 0 to 2 pi or minus pi to pi. Okay. So it's the bottom line is it's periodic with the period 2 pi. On the other hand, this chap here, can you comment on this spectrum? Is it periodic or is it not periodic? This is also periodic with period 2 pi by t radians per second. And for those of us who like to talk about things in terms of hertz, this is periodic with 1 by t, which is the sampling rate. Does it make sense? So if, for example, the maximum frequency content of x of t was 1 over 2t. So make this all in radians per second, so I will make it 2 pi by 2t, and this is 2 pi by 2t. If I sample this at a rate 1 over t, what will happen? The spectrum excess of t will become okay. So you can see that the spectrum basically repeats at 2 pi by t. This is, so if I wanted to plot x of e to the j omega, what would I do? please note that omega t has to be replaced by omega. So in other words, I multiply the x-axis by, multiply the x-axis here by t. Okay. So this becomes pi, this becomes 2 pi, this becomes 4 pi, and so on, and this becomes minus pi, minus 2 pi, minus 3 pi, and so on. Okay, this is the discrete time spectrum. And as you can see, this situation corresponds to a sampling rate which is exactly the Nyquist rate. Okay, so when you look at the discrete time spectrum, you see that it occupies the entire range from 0 to minus pi to pi, or 0 to 2 pi. There is no hole in the spectrum at all, right? If you sample this at a rate any smaller than 1 over t, then you will find that there will be these aliases will all overlap, causing some aliasing in the spectrum. If x of t is not band limited, then what can you expect to happen? Once you sample, there will be aliasing. So there will be aliasing. Aliasing is basically many continuous time frequencies all masquerading as the same discrete time frequency. Okay. So the question is there any specific relationship between these many frequencies in the continuous time domain which all map to the same discrete time frequency? So how will you figure that out? From this relation, so all alias to the discrete time frequency omega. Okay. In English, it means that all tones which are spaced by the sampling rate will all get back to the same tone in the discrete time domain. Does that make sense? For example, if you are sampling a 1 kilohertz sine wave at say 10 kilohertz, how will this look in the discrete time domain? What will the corresponding discrete time frequency be? A sine wave at 1 kilohertz is sampled at 10 kilohertz to get a discrete time sequence. It's also a discrete time sinusoid. What do you think the frequency of the discrete time sinusoid will be? 2 pi by 10. Why? So the sampling rate corresponds to, the sampling rate fs corresponds to 2 pi. Alright. So that basically means 10 kilohertz corresponds to 2 pi, which means 1 kilohertz will correspond to 2 pi by 10. Okay? Alright. Now, what do you think 11 kilohertz will correspond to? You have 11 kilohertz sine wave sampled at 10 kilohertz. It will also correspond to 2 pi by 10. And so will 21 kilohertz sampled at 10 kilohertz will also look like 2 pi by 10. It's pretty straightforward. Physically what's happening is that, let's say this was the original sine wave and it was being sampled, say, at these points. Okay. When you say aliasing, it basically means that you can draw any number of sine waves which pass through all these points. That's all that aliasing is. Real signals have noise. So, if the signal band was, say, restricted to plus minus B, and if I sampled this signal at rate Fs, the spectrum would repeat. All this is now in hertz, so this should be Fs. Okay? And so basically what does it mean? B will correspond to a discrete time frequency of 2 pi times B by Fs. Okay? But to this frequency will also alias any component that happened to be in the input signal at frequencies that are separated from B by Fs. So anything in the range minus B plus B is the original signal plus K times Fs will all alias back into the same frequency range in the discrete time domain, will alias to 2 pi times B by F. So even though the input signal just happens to be plus minus B, as I discussed yesterday, there is going to be, all signals are accompanied by noise, and this noise need not necessarily be confined to the signal band. Okay. It could have components with frequency content much higher than B. And in this picture it is shown in green, so this corresponds to noise. Okay. So when I sample signal at a rate Fs, where all should I be worried about noise? Signal components in a frequency band Fs plus minus B, once you sample it at a rate Fs, frequencies, noise in this band will all alias into the signal band once you sample the signal. Yesterday what did we see, what did we say that we should do to avoid this problem of noise folding back into the signal bandwidth? So you put an anti-alias filter. So this is the frequency response of the anti-alias filter. Okay. Now let's consider two situations. We have the signal bandwidth being the same in both cases, minus B to B, minus B to B. In one case, this is my Fs, Fs1. In the other case, this is my sampling rate. Alright. In case A, what are the bands? Noise will alias into the signal band once I sample. Fs1 minus B to Fs1 plus B. Correct? So in case B it is Fs2 minus B to Fs2 plus B. So if I need to put an anti-alias filter, in the first case, I want to make sure that my anti-alias filter doesn't screw up my in-band signal. So it must be flat within 0 to B. Okay. Then ideally what must it do? It must fall off as rapidly as possible. Ideally it must be a rectangular, it must be a brick wall filter. But you know that a brick wall filter is impossible to realize. As you go on increasing order, you can only get sharper and sharper cutoff. You can never really get something which falls off obviously infinitely fast. So if you want the same degree of alias rejection, noise rejection due to aliasing, the anti-alias filter spec here, let's say this is a log scale. So the filter response is plotted on this is log magnitude of the filter response. Okay. So what can you say about case 2? A cheaper filter will do, because if I use the same filter, you can see that the rejection I get is much larger when compared to the rejection I get in case A. Does that make sense? For the same anti-alias filter, better noise rejection, in case B. Alright? If I want the same noise rejection, case A needs a much sharper filter, when compared to case B. Does that make sense? Okay. So the choice of sampling rate needs to consider the design of the anti-alias filter. Nyquist is telling you that if you have the signal has got a bandwidth B, you can sample at a rate as low as 2B. But if you did that's only possible if you have an anti-alias filter which is infinitely sharp. Obviously a very, very sharp filter is difficult to design, and for those of you who have taken the elective on filters, you know that when the order of the filter is high, the noise generated inside the filter is high and it's more sensitive and a whole bunch of other things. Okay. So even though Nyquist is telling you that 2 times B is enough, in practical systems you will find that the sampling is always done at a rate higher than Nyquist. Okay. If the signal bandwidth is B, then the Nyquist rate is B. Okay, and the ratio of the sampling rate to the Nyquist rate is quite logically called the oversampling ratio, where the reason behind the name is that the signal has got a bandwidth B. Nyquist is telling you that you need to only sample at 2B. However, you are actually doing it at a rate Fs which happens to be larger than the Nyquist rate, so you are oversampling the signal by some factor which is Fs by the Nyquist. So this OSR is something that you will see repeatedly in this course. Okay, a larger OSR implies simpler or cheaper anti-alias. In practical systems, things are always oversampled to some degree. When the signal bandwidths to be digitized are low, it is fairly straightforward to design sample and holds. To design circuits which accomplish sampling, which sample at very, very high speeds. Okay, so you can, when the signal bandwidth B is low, it's fairly straightforward to get a large oversampling ratio. Okay. On the other hand, when the signals to be digitized are themselves very, very wideband. For example, in oscilloscopes, where whenever you want to test any system, you basically must have measurement equipment which must be as fast or even faster than the system that you are trying to test. So a classic case is wideband oscilloscopes, where the bandwidths can be, the signal bandwidths that they can digitize can be anywhere, depending on how much you pay, can be as high as 20 or 30 gigahertz. Okay, and in such cases it becomes obviously extremely difficult to oversample by a very large degree. You try to be as close to Nyquist as possible, sampling rate and oversampling. It turns out that in many cases it is not possible for the circuits which, for the stuff that goes into the sample and hold. Finally, this all has to be implemented in hardware. So you need transistors, to do various, to accomplish various tasks in the sampling operation. And it turns out that when the sampling rates are extremely high, okay, you will find that transistors there is finite speed associated with transistors, so they're just not able to do whatever they're supposed to do at very, very high rates. So in other words, there is a finite limit to the rate at which you can sample in practice. And clearly this depends on the speed of the transistors. So if the transistors are fast, presumably you can sample faster. So now the question is, what happens if you want to sample at a speed Fs, okay, but your sample and holds are only good to, cannot sample any more than at a rate Fs by 2. Do you understand? The question is, I want to sample at a rate, say, 1 gigahertz, okay, but my transistors are all lousy and very slow, which means that after doing a lot of study, I have found that any sampling rate greater than, say, 500 megahertz is not possible. Okay? So the question is there anything I can do? So one way of doing this is to say, hey, if I had, let's say, I am sampling at the rising edge of a clock, okay. If I had two sample and holds which are slow, I can effectively double my speed by, okay, this is a signal, I need to sample it every time interval t seconds. My sample and hold, unfortunately, is a lazy bum and can only do it every 2t seconds. So then what do? I can put two sample and holds. One sample and hold corresponds to is sampling at a rate of 1 over 2t. The other sample and hold is sampling at a rate also 1 over 2t. However, the sampling instance of both these slow sample and holds are separated by a time instant t. So in other words, you can use, two slow sample and holds to equivalently sample at a effectively larger rate. Okay, and the same thing can be extended to m sample and holds. If I had m identical sample and holds which can only run at a much lower rate, I can put many of them together, skew their sampling instance in time, okay, and get these m guys to equivalently sample at a much higher. N equal to 2 case, you can see that, this is often called a ping-pong approach, because the each sample and hold, the first guy is called ping and the second guy is called pong, okay, and they process alternate samples, and looking at the outputs of the two, you can, so we'll continue tomorrow.